In most modern data centers, keeping tabs on server health means installing software agents directly onto the machine's operating system. These agents constantly report back on memory usage, CPU load, and overall performance. But this software-level view relies entirely on two things going perfectly right. First, the main production network has to be actively routing traffic. And second, the operating system itself has to remain stable. When that operating system becomes overloaded, unstable, or completely freezes up, those software agents go down with it. The flow of telemetry data simply stops. Relying strictly on the OS for monitoring creates a massive vulnerability. Right at the exact moment a catastrophic failure begins, the system meant to warn you goes completely dark. Long before a server completely crashes, the physical hardware begins to fail in stages. A power supply voltage might fluctuate, memory modules throw microscopic errors, or a cooling fan spins just a few revolutions per minute too slowly. These physical component faults happen quietly in the background, appearing days or even weeks before a visible service outage actually hits the business. If one of those hardware faults eventually causes the operating system to lock up, the standard monitoring agents are instantly disabled. They cannot transmit the warning signs that preceded the freeze. As a result, IT operations teams are left unaware that hardware is actively dying in their racks. Their monitoring dashboards look fine, leaving them to wait for an end user to report that the system is down. Preventing these outages requires a secondary warning system. You need a layer of monitoring that sits underneath the software and bypasses the operating system entirely. This is where out-of-band management comes in. It operates as an autonomous monitoring layer, running directly on the physical hardware, completely insulated from the status of the operating system. This diagram shows how that separation works on the motherboard. While the primary processor handles the operating system, there is a separate microchip called the Baseboard Management Controller, or BMC. This chip acts as the server's independent brain specifically for hardware health. The BMC doesn't share the same communication lines as the OS. It transmits its health data out over a dedicated management network, bypassing the main production network entirely. When the BMC detects a physical fault, it generates a specific distress signal called a Platform Event Trap, or PET. This is a hardware-level alert designed specifically to report on these low-level conditions. Because of this out-of-band architecture, the BMC transmits that PET distress beacon successfully, even if the server's main processor is completely dead. Let's look at exactly how this timeline plays out. Imagine an industrial cooling fan inside a server unit violently shudders and grinds to a halt, dropping well below its required RPM. The instant that rotation slows down, the BMC registers the physical RPM drop. Milliseconds later, it records the resulting temperature spike rising off the processor. Operating entirely on its own, the BMC takes that temperature and fan speed data and packages it into a platform event trap. That trap is then fired across the isolated management network, typically using standardized delivery protocols like IPMI or specific SNMP trap mechanisms. This same autonomous process kicks in for a variety of critical physical events, from unauthorized chassis intrusions to unexpected BIOS changes or firmware faults. Operating entirely outside the software layer, platform event traps serve as an unblockable, hardware-driven SOS. They provide the earliest possible detection that physical infrastructure is failing. But simply generating these alerts introduces an operational challenge. Raw platform event traps and SNMP data are machine-level protocols, not written to be immediately readable by a human operator. In practice, the raw output looks like this. It is a high-volume stream of unformatted hexadecimal terminal codes that are wildly inconsistent depending on the hardware vendor. Even if an engineer manages to decode the text, this raw data lacks critical business context. The trap tells you a fan is dead, but it offers no information on what specific application or service that dying hardware actually supports. Receiving a flood of these raw hardware traps is operationally difficult. Without a centralized system to translate the codes and prioritize the signals, the warnings just become more noise. Sensaka acts as the intelligence engine required to capture, translate, and manage all of this out-of-band hardware telemetry. In this diagram, we can see how the platform ingests inconsistent PET data. Sensaka automatically parses those vendor-specific codes so that they emerge cleanly as normalized alerts in a uniform format. Sensaka connects that normalized warning directly to the physical rack location and the specific lifecycle history of the asset. By filtering out the vast amounts of routine informational noise, the system ensures that only isolated, actionable critical failures reach the centralized alarm view. By accurately decoding platform event traps, Sensaka gives infrastructure teams a precise map of their hardware health. They can quickly locate and neutralize a microscopic component fault before it escalates into a catastrophic business outage.